In digital electronic flip-flops are widely used for handling binary information. From the flip-flop family, Jack-Kilby flip-flop JK flip-flop is versatile and can be used as a basic memory element. It can also store toggle functionality with a diversity of making applications with it. What is JK flip-flop? It is one kind of sequential logic circuit which stores binary information in bitwise manner. It consists of 2 inputs and 2 outputs. Inputs are set J and reset K, and their corresponding outputs are Q and Q. JK flip-flop has 2 modes of operation, which are synchronous mode and asynchronous mode. 2 3-input NAND gates are used in place of the original 2 2-input AND gates. The outputs at Q and Q are coupled to each gate's 3rd input. Since the 2 inputs are now interlocked, the SR flip-flop's cross-coupling enables the previously invalid condition of S equals 1, R equals 1, to be employed to perform the toggle action. In a circuit set, the bottom NAND gate interrupts the J input coming from the 0 position of Q. In the reset state, the top NAND gate interrupts the K input coming from the 0 positions of Q. We can use Q and Q to control the input because they are always different. The flip-flop is toggled according to the truth table when both inputs J and K are set to 1. A JK flip-flop is a kind of sequential logic circuit that keeps track of binary data. Its characteristic table shows how the output, Qn+1, changes using inputs, J and K, along with the last state, Qn. There are 4 states to understand: J equals 0, K equals 0, no change. Here, the output Qn+1 stays the same. This means the next state, Qn+1, is just like the current one, Qn. J equals 0, K equals 1, reset state. In this case, the next state is reset to 0, Qn+1 equals 0, no matter what the current state is, Qn. J equals 1, K equals 0, set state. Now, the next state gets set to 1, Qn+1 equals 1, again, no matter what's happening in the current state, Qn. J equals 1, K equals 1, toggle state. In this state, the output Qn+1 toggles. So if the current state is set, Qn equals 1, it will change to 0, Qn+1 equals 0. If it's reset, Qn equals 0, then it flips to 1, Qn+1 equals 1. Characteristic equation, KQn plus JQn. The excitation table shows us which input combinations we should use for a JK flip-flop to get the output we want. X, don't care Qn, current state Qn+1, next state J and K, 2 input values here, X for don't care. This means it can be either 0 or 1, and it won't change how the flip-flop works. This table guides us on what input values to use so we can move from the current, Qn, to the next state, Qn+1. Let's look at the transitions from 0 to 0. When the current state is 0, Qn equals 0, and you want the next one to stay 0, Qn+1 equals 0, then set J equals 0 and K can be either 0 or 1, which is shown as X, don't care. From 0 to 1, if the current state is 0, Qn equals 0, but you want the next state to flip to 1, Qn+1 equals 1, then J should be set to 1 and K equals X, doesn't matter for K. From 1 to 0, when you start with a current state of 1, Qn equals 1, and wish for it to switch to 0, Qn+1 equals 0, then J should be X and K must be set at 1. From 1 to 1, if you're at a current state of 1, Qn equals 1, and want it to stay at 1 for the next state, Qn+1 equals 1, then just set J equals X and K should be set at 0. This table is used a lot in circuit design. It helps show the inputs needed to get those desired output transitions.